Hello everyone, I'm Marcelo Amaral from IBM Research Tokyo. I'm going to introduce the Kepler architecture. Kepler is the efficient power level exporter based on Kubernetes project. Here's the list of the contributors. Sorry if I'm missing someone. Okay, so Kepler is a framework that is composed by multiple power models that can be applied to various scenarios. For example, for different CPU architecture or using different metrics, depends on the metric availability. The Kepler frameworks aims to provide public available power model from the community to be shared with the community. That is, the community can share data from different CPU architecture. We can create power models for that, and this can be reused for the community in different contexts. So our modeling approach can use different power metrics from various power sources. For example, the Intel RAPL that collects the power consumption of the CPU and the DRAM typically, and also the motherboard sensor that collects the energy consumption of the entire motherboard and can be accessed by the ACPI sensors, and also the hardware counters that we collect using eBPF, and where eBPF is a tool that enables the kernel extension without the need to recompile the kernel. So we can collect metrics more efficiently with eBPF. Okay, so the different power models can be created and applied depends on the context. So if the system has real-time power metrics or hardware counters or not. For example, if it's running directly in the bare metal, it's running on the VMs, but of course, the availability of the metrics impacts in the occurrence of the model. Okay, so to ensure fairness in our power model, we follow the green gas protocol recommendation, that is, split the constant power, which is the idle power, based on the user resource allocation, and the dynamic power based on the resource utilization. So additionally, Kepler has low overhead when collecting the hardware counters because of the in-kernel implementation using BPF, as I mentioned before. Kepler is composed by multiple modules that can be optionally deployed. For example, the main module is the metric exporter, and the other modules can be optionally deployed depends on the context. The metric exporter module collects metrics and calculates process and container power consumption. So the metric exporter module has internally two different power models. The ratio that uses CPU instructions to divide the dynamic power among the process, and the linear regression that uses more metrics than only CPU instructions, but needs to be pre-trained for a given system by collecting metrics. And for more advanced power models, for example, using algorithms for linear regression, we have the model server and energy estimation. So the model server receives data from the metric exporter to train the new power model. Okay, so and this can train the new power model can be trained using nonlinear regression algorithms. And the energy estimation model receives the power model pre-trained parameters along with the process resource utilization to calculate the power consumption. So in this case, both the model server and the energy estimator are implemented in Python because Python has more available statistics libraries. Okay, so just an overview how everything is done, how the whole process works. First, all the select First we select the a set of widely available metrics, such as CPU instructions, cycles, cache, what's the metrics that will be used for the power model. Then Kepler first calibrates to discover the idle power consumption. So, it can vary for different systems. The idle power is used to calculate the dynamic power, and then by having the dynamic power and the resource utilization, we run the regression algorithm to create the power model. The output of the regression algorithm is actually the power model that we use it for inference to calculate the energy consumption of containers. Okay, so thank everyone for the attention. This is the introduction of the Kepler architecture.